Welcome to part 2. Here we're going to talk about the fundamental trigonometric limit. In part 1 we talked a little bit about the Squeeze Theorem, and here we're going to apply it to prove this limit here. We're going to prove that the limit as x approaches 0 of sine of x over x equals 1. And to that we're going to use a little bit of geometry, and then we're going to apply the Squeeze Theorem. So you're going to see why the Squeeze Theorem is useful. So we're going to start with this picture here. This is the unit circle. That is the circle with radius 1. And we're going to draw this radius here and this triangle here. And we're going to call this angle x. And we're going to give names to this point here. I'm going to draw this line and this line. And well, we want to apply the Squeeze Theorem, and to do that we need an inequality. So what we're going to do is to use this inequality between areas. Here we have, this means the area of the triangle MOA. Here we have the triangle MOA. Here is this triangle here. And this inequality says that the area of this triangle is less than the area of the sector MOA. The sector is the slice of pizza here. The slice of pizza contains the triangle, so its area must be bigger than the area of the triangle. And the slice of pizza, there is the circular sector, is contained in this bigger triangle. That is triangle COA. That's why we had this inequality. And what we're going to do now is to express these areas in terms of trigonometric functions in this triangle. So we're going to write to an inequality between trigonometric functions. So let's begin with the area of the triangle MOA. And to do that we're going to calculate the sine of x, the sine of this angle here. Sine of x is this side over this side. And well, we have that sine of x is Bm, this side over this side, but this side is the radius of the circle, so it equals 1. And we have the sine of x equals Bm. Now the area of the triangle MOA is base times height over 2, and base, the base of this triangle is the radius of the circle, so it is 1. The height is Bm, but Bm equals sine of x, so we have that this area is sine of x over 2. Now we can replace the expression we got in this inequality. We can replace this area of the triangle by sine of x over 2. So we do that, and now we're going to try to replace this area of the triangle COA. So we're going to calculate the tangent of x. Now here we can calculate tangent of x as this side AC over the side OA. But OA is the radius over this one, so we have that tangent of x is AC. Now the triangle, the area of the triangle COA is base times height over 2. The base is 1 and the height is AC. That will show that AC is tangent of x. So we get that the area is tangent of x over 2. Now we can replace here the area of COA by tangent of x over 2. We do that, and we get this inequality. The only thing left to do is to replace this area of the sector. And to do that we're going to remember how to calculate the area of the circular sector. The area of the circular sector is given by this formula here. Here theta is the angle of the circular sector, and r is the radius. So a simple proof of this little formula is the following. Consider that if you have a circular sector of radius 2 pi, the area is the area of the circle, there is pi times radius squared. Now if we multiply both sides of this equation by theta over 2 pi, on the left side we get this, and we can introduce this factor inside the parentheses here. We can cancel out 2 pi and get that this will be the area of a circular sector of angle theta. On the right side we multiply this by this factor, we can cancel the pi, and we get this expression of the formula. So you can see why this formula is true. Now let's apply this formula to this circular sector. For this sector the angle is x and the radius is 1. See, here we go. So replacing in our formula we have x times radius squared, that is 1 squared over 2. That is x over 2. That's simple. We can replace that in this inequality, and we get this inequality. Now we can multiply everything by 2, and now we got it. We got our inequality between trigonometric functions and x, right? Now we're going to forget about that picture, we're going to forget the geometry, and we're only going to deal with this inequality. And to do that we're going to first divide everything by sine of x. If we do that in this side we get 1, here we get x over sine of x, and here we get 1 over cosine of x. Now we can change the direction of the inequality by taking the inverse of each of the members here of the inequality. We do that here. If the inverse of 1 is 1, the inverse of this is the sine of x over x, and the inverse of 1 over cosine of x is cosine of x. So now we're ready to apply the squeeze theorem. Here we have sine of x over x squeezed between 1 and cosine of x, and we can consider 1 as a function that has limit 1 when x approaches 0, and cosine of x also approaches 1 when x approaches 0. So by the squeeze theorem, here we get that cosine of x approaches 1, and by the squeeze theorem the limit of sine of x over x when x approaches 0 must also be 1. That's just the squeeze theorem. So that's it. To review what we had done, we started with this geometry here, and using just trigonometric functions and calculating areas we got this inequality here, and then working a little bit with the inequality we got to this inequality. And here we apply the squeeze theorem and use the fact that cosine of x approaches 1 when x approaches 0. So sine of x over x becomes squeezed between these two functions that approach 1, so it must also approach 1. And this is a very important limit that will allow us to calculate all types of trigonometric limits. So that's all for now. Thank you for watching, and see you next time.